Okay, now that we have the fundamental theorem of arithmetic, we can explore greatest common divisors a bit more and actually come up with some pretty efficient and quick proofs for the results that we need about the greatest common divisor. Let's have a look. Okay, well, first of all, we've got to remember the greatest common divisor, mn of m and n, is the largest positive integer d, so that d divides m and d divides n. And well, yeah, that's pretty much it for an introduction. That's what we're going to talk about. So the first result is actually fairly quick. If you've got two integers so that one of them is not equal to 0, then there are integers p and q so that q is not equal to 0, and so that p and q have greatest common divisor 1, so that a over b is equal to p over q. Basically, what this proposition says is that fractions can be written in lowest common terms. And well, it's actually pretty easy, right? You just take numerator and denominator and divide them by the greatest common divisors. So if you let d be the greatest common divisor of a and b, then you use p being a over d and q being b over d. Well, then p over q is a over b, and p and q can't have any common divisors except for 1, because if they had another common divisor, then that would divide a and b also, and d would not be the greatest common divisor of a and b. So that's fairly quick, and the next one isn't so quick anymore. But we also want to talk about what happens when you start forming linear combinations of numbers, and in certain situations, greatest common divisors get preserved. For example, when you've got three integers a, b, and c, then the greatest common divisor of a and b is also the greatest common divisor of b with a plus cb. So basically, adding a multiple of b to a doesn't change the greatest common divisor of that with b. And to prove that, well, we take an integer, and we're just going to show that in fact these two numbers have the same divisors, and that then also means that they will have the same greatest common divisors. So you take an arbitrary integer, and well, then we know that d divides a and d divides b if and only if d divides a and d divides b and d divides c times b, and that's because, well, the direction from here to here is quite trivial, and the opposite direction, of course, if d divides b, then d must also divide any multiple of b, so there's not much there. Well, that's the case if and only if a is a multiple of d, b is a multiple of d, and cb is a multiple of d. No problem, that's just straight from the definition of what it means that one number divides another number. That's the case if and only if, well, let's see. We've kept the equation for b, we've kept the equation for cb, and we've added the equation for a and for cb to get an equation for a plus cb, so that means the top does imply the bottom. And if I subtract the equation for cb from the equation from a plus cb, I can also get back to the top line here. So again, that is an if and only if. Well, and that's the case if and only if a plus cb is divided by d and b is divided by d. And yeah, that's, if we go from the top to the bottom, we've just dropped one equation. And on the other hand, if we want to go from the bottom to the top, if we just multiply the equation for b with c, we get the equation for cb. But this, of course, just means that d divides, it's the same as d divides a plus cb and d divides b. And so that means that these two numbers and these two numbers have the same divisors, and that means in particular they must have the same greatest common divisor. Okay, so now we're again talking about two integers that are not both 0, and we want to characterize the greatest common divisor. And a positive integer d is the greatest common divisor of a and b if and only if, first of all, it divides both of them, and second of all, it is being divided by every number that divides both a and b. So if c is an integer that divides a and b, then c also divides d. And we prove that with the fundamental theorem of arithmetic. So by the fundamental theorem of arithmetic, we know that a has a factorization as a product pj to the aj, and b has a factorization as a product pj to the bj, where the pj are pairwise distinct prime numbers, and the aj and bj could be 0, because we want to have the same factors in both. And by that, we have, of course, that the greatest common divisor of a and b is the product j equals 1 to k p to pj to the minimum of AJ and BJ. And so now we're going to use that to prove both directions, namely that greatest common divisor must have properties 1 and 2, and that anything with properties 1 and 2 must be the greatest common divisor. So first we start with D being the greatest common divisor. And we know that the greatest common divisor divides A and B, so that means 1 is not an issue. And if we have a number C, so that C divides A and C divides B, well then the prime factorization of C can only contain primes from among the P1 through Pk, because otherwise it wouldn't divide A or it wouldn't divide B, and it can't contain any of those with an exponent larger than the minimum of AJ, BJ, because again otherwise C would not divide one of A and B. And that means that C divides the greatest common divisor of A and B because all the prime factors in C occur in the prime factorization of the greatest common divisor, and they occur with equal or lesser exponents. Okay, the direction right to left, so now we're assuming that D divides 1 and 2, and we want to prove it's the greatest common divisor. Well, let D be so that D divides A and D divides B, and so that if C is an integer that divides A and B, then C divides D. Well, then the prime factorization of D can only contain primes from among P1 through Pk because D divides A and D divides B, and none of them with an exponent larger than the minimum of AJ and BJ, again because D divides A and B. But now we also know for every J that Pj to the minimum of AJ, BJ divides A and it divides B. That means it can act as one of those C's here, and that means Pj to the minimum AJ, BJ also divides D, and that means that every exponent is also at least the minimum of AJ and BJ, and that means that D must be the greatest common divisor of A and B because its prime factorization consists of the Pj's raised to the exponent AJ, minimum of AJ and BJ. And that's the proof of that. So now we have a nice characterization of the greatest common divisor that only uses divisibility. We don't have to worry about inequalities anymore. Now, inequalities aren't that bad, but once you start working with arithmetic properties of numbers, it is natural that you want to express everything in terms of divisibility, including a characterization of the greatest common divisor. Okay, we still haven't answered how you actually get the greatest common divisor effectively, but that is happening now because Euclid's algorithm does exactly that. So we let m and n be integers, and we claim that there are integers s and t, so that sm plus tn is the greatest common divisor of m and n. Well, so again, we've got one of those theorems like the division algorithm that claims something algorithmic, and yet the theorem itself just states something exists, and that's because the algorithm is actually the proof. So let's take a look at the proof. We let a0 be m, and we let a1 be n, and now we're going to recursively construct more numbers aj. Namely, once we've got aj minus 1 at aj, and in the base step we would have j equals 1, and we would have a0 and a1, right? So once aj minus 1 and aj are chosen, there is a quotient that is an integer, and a remainder aj plus 1 that is a non-negative integer, so that aj minus 1 is equal to qj aj plus aj plus 1. So that's just division with remainder, where aj plus 1 is strictly is a natural number or 0 that is strictly smaller than the absolute value of aj, or aj plus 1 equals 0. And yeah, that's just straightforward division with remainder, and we're very quickly going to end up with just natural numbers. But in the first step, the a1 could be negative, so we have to use absolute values here. So basically what we do is we always take the last two numbers that this algorithm has generated, and we divide the smaller one, the larger one by the smaller one. We stop that construction at the j equals k, where ak plus 1 is equal to 0. After all, we are constructing a decreasing sequence of natural numbers. At some point in time, that thing is going to stop. So at some point in time, we're going to just hit 0 here. Well, then what do we know? We know that ak divides ak minus 1, because ak minus 1 is just qk times ak, right? Because ak plus 1 is 0. And that means that AK divides AK minus 2 because AK minus 2 was QK minus 1, AK minus 1, AK, right? And so AK certainly divides itself, and we've just seen that it divides AK minus 1, so it now divides AK minus 2. Well, if it divides AK minus 1 and AK minus 2, then because AK minus 3 is a linear combination of those two, it must also divide AK minus 3, and so on and so on. So ultimately what we can see here is that the number AK divides all the AJ, and in particular AK is a common divisor of m equals A0 and n equals A1. Well, so now we still have to show that that this is somehow the, well, okay, we want to show basically that AK is the greatest common divisor, and then we're going to worry about the Sm plus Tn. Yeah, okay, so if P divides M and P divides N, well, then P divides A0 and P divides A1. And that means P divides A2 because A2 is just A0 minus Q1 A1, and that's just taking this equation and solving for AJ plus 1, right? And so that implies that P divides A3, which is A1 minus Q2 A2. Again, we just keep solving for the last one. And that keeps going, and so that means P divides AK. And that means every common divisor of M and N divides AK, which means that AK is the greatest common divisor of M and N. Okay, so that is the part of the algorithm that produces the greatest common divisor. You just keep doing those divisions, and we're also going to see an example. But what you end up with in the last step is the greatest common divisor. And the interesting thing is that for all j from 2 to k, we have that aj is aj minus 1, aj minus 2 minus qj minus 1 minus times aj minus 1. And that's just this equation up here, where we solve for aj plus 1 and then shift the index. That's all that happened there. And basically what that means is that AK is AK minus 2 minus QK minus 1, AK minus 1, but now I can express AK minus 1 in terms of the earlier A's, right? So this is AK minus 2 minus QK minus 1 times AK minus 3 minus QK minus 2 times AK minus 2, and that would express AK in terms of AK minus 2 and AK minus 3. And we would build ourselves back up all the way until we have some number times A0 plus some number times A1, which is exactly the Sm plus Tn. And that concludes the proof here. So we have found an algorithm that spits out the greatest common divisor, which is the AK, and which ultimately expresses that, can be used to express the greatest common divisor as a linear combination of the two numbers. Let's see how that works. So if we want to compute the greatest common divisor of 3,526 and 301, what do we do? And we also want to find the numbers S and T, so that the greatest common divisor is S times 3,526 plus T times 301. Well, we have to divide A0 being 3,526 by A1 being 301. And that ends up being 3,526 being 11 times 301 plus 215. Let's see. 10 times 301 is 3,010, so that would be 3,311 plus 215 is 3,526. Yes, that is correct. Now we divide 301 by 215. And, well, of course, 301 is just 1 times 215 plus 86, right? Because 6 added here gives us 221 plus 80 gives us 301. Yes, that's correct. Now we divide 215 by 86. 86 could go in twice, should go in twice. So dividing 215 by 86 gives us 215 equals 2 times 86 plus 43. Let's see. 2 times 86 is 172. Plus 3 is 175. Plus 40 is 215. Yes, that's correct. So we divide 83 by 43 and 86 by 43, and division of 86 by 43 gives that 86 is 2 times 43 plus 0, and remember that's where the algorithm was supposed to stop, so we know now that 43 is the greatest common divisor. And yeah, now we want to have the numbers that represent it. So now we just go and solve backwards. 43, if we just solve for 43 in the second to last equation, we get that that's 1 times 215 plus negative 2 times 86. And now we can solve for 86 in the next higher equation. We realize that this is 1 times 215 plus negative 2 times what 86 was, namely 301 plus negative 1 times 215. And so that should give us 3 times 15 plus negative 3 times 215 plus negative 2 times 301. Now we can express 215 in terms of 301 and 3,526, namely 215 was 3,526 plus negative 11 times 301, the whole thing times 3, and we still have negative 2 times 301 over here, and that gives us 3 times 3,526 minus 35 times 301. And that means the numbers are s equals 3 and t equals negative 35. Okay, so that's Euclid's algorithm. And we're going to talk a little bit about these linear combinations now. I've already used the verbiage. Well, a linear combination of integers a and b is a sum of the form sa plus tb, where s and t are integers. Sure, what else would it be? So we now have some corollaries from Euclid's algorithm. And that is the greatest common divisor of two integers a and b that are not both 0 is the smallest positive integer that is a linear combination of a and b. Well, the proof is fairly simple. We already know that the greatest common divisor is a linear combination of a and b, and so all we have to show is that if d is a number between 1 and the greatest common divisor of a and b, that is also a linear combination of a and b, well, then we have to show that that's the greatest common divisor. But we know that the greatest common divisor of a and b divides sa plus tb because it divides a and it divides b. And that means ab divides d, and that means that d must be the greatest common divisor of a and b because that's the only number between 1 and the greatest common divisor of a and b that that is divided by the greatest common divisor of a and b. Okay, well, we also have a little theorem, namely two integers are relatively prime if and only if they are integers s and t, so that sa plus tb is equal to 1, and that's just the preceding corollary, right? We know that the greatest common divisor of two numbers is the smallest possible positive integer that is a linear combination of a and b, and if 1 is a linear combination of a and b, well, then that certainly is the smallest positive integer that would be a linear combination of the two, and that means 1 is the greatest common divisor of a and b. Okay, further consequences. The set of linear combinations of two positive integers a and b is the set of integer multiples of the greatest common divisor. Sure. If x is so that there are s and t so that sa plus tb equals x, well then, because the greatest common divisor divides sa plus tb, we must have that the greatest common divisor divides x, and that means that x is an integer multiple of the greatest common divisor. Okay. And, well, we can also define greatest common divisors for more than two numbers. When you have integers a1 through an that are not all 0, we can define the greatest common divisor to be the largest integer that is a divisor of all of them. And it's denoted parenthesis a1 through an, parenthesis closes, so the same notation as for the greatest common divisor of two numbers. And as an example, the greatest common divisor of 30, 42, and 45 is 3, and that's because 30 is 2 times 3 times 5, 42 is 2 times 3 times 7, and 45 is 3 times 3 times 5. And the only number that occurs here in all of these factorizations is 3, and it only occurs once in two of them, so 3 must be the greatest common divisor. Quick lemma. When you've got integers a1 through an that are not all 0, then the greatest common divisor of a1 through an is the greatest common divisor of a1 through an minus 2 and the greatest common divisor of an minus 1 and an. So that means the greatest common divisor of n integers can be computed iteratively. We would just pairwise form greatest common divisors and work our way back down the chain. And the proof is, well, ought to be fairly simple, namely a1 through an minus 2 and an minus 1 an. So this number here, that is the greatest common divisor of a1 through an minus 2 and the greatest common divisor of an minus 1 and an, that is the largest integer that divides all the ai from 1 through n minus 2, and it is the and that also divides the greatest common divisor of an minus 1 and an, and that is the largest integer that divides all the ai. Well, it certainly divides all the ai, and if there was an integer that is larger that divides all the ai, it would also divide the greatest common divisor of an minus 1 and an, and so it would be a greatest common divisor of these, it would be a divisor of these numbers here. So that means that this number is the largest integer that divides all the ai, and the largest integer that divides all the ai is the greatest common divisor of the ai. And so that's already the proof here. And so the numbers 10, 42, and 45 show that several numbers can have a greatest common divisor of 1 even if none of their pairs do. Yeah, and that is because, let's see, 10 and 42 are both divided by 2, 10 and 45 are both divided by 5, and 42 and 45 are both divided by 3, but so that means any two of them have a greatest common divisor that is not 1. However, 10 is 2 times 5, and 5 is not in the factorization of 42, and 2 is not in the factorization of 45, which means that the greatest common divisor of these three numbers really is 1. So that means we have to distinguish between mutually relatively prime numbers and pairwise relatively prime numbers. Namely, the numbers are called mutually relatively prime if their greatest common divisor is 1. So 10, 42, and 45 are mutually relatively prime. However, the notion of pairwise relatively prime now is something else, namely numbers are called pairwise relatively prime if and only if any two distinct numbers have greatest common divisor 1 between them. And yeah, that is already it, and we can certainly see that 10, 42, and 45 are not pairwise relatively prime. So pairwise relatively prime is the stronger notion. It's also fairly easy to see that it implies that the numbers are mutually relatively prime. Okay, that was a quick run through some relevant results about greatest common divisors that we will be using in the future. Among them, certainly not to be underestimated, Euclid's algorithm, which is a fast algorithm to compute greatest common divisors, which will come in very handily when we're talking about cryptography, for example. All right, thank you very much.